Greetings, everybody. I'm going to talk about high-speed addition today. It's November 17, 2014, and this is something that we covered last Monday and Wednesday, so this will be on video on YouTube after I record this particular session. So let's just start by talking about the notion of adding two unsigned integers. And in this case, our goal is to generate a vector of n bits, which we call the sum bits here, which are equivalent to the summation on the right-hand side. As you can see that the weights are introduced, 2 to the i's are introduced into the sum. So clearly the bits have different significances, and that is just indicated by the weight that we associate with the ith bit, or the bracketed s bit here. And we then take our two operands, u and v, and then write them out in the same way. And our goal is to generate the sum of these two n-bit numbers. They're binary expressed. And so in order to do this, we introduce a carry vector, which is sort of like an n plus 1 bit vector. The last carry is really the carry from the entire computation, but all the other carries are needed to perform the addition itself simply by examining this expression down here. So the sum of the two numbers that we're adding are expressed as the sum of the summations that they're represented with over here, as you can see. And that sum is then written out by combining the terms together into a single sum. And then noting that when we add two bits here, we could potentially get a number that would be outside of the representation of a single bit. And for that, we need to introduce this carry bit, which we created here, and we put that into the summation. And then now we have to mod to reduce it so that whatever we get out of this summation is actually nothing but a 0 or 1. And that's how we get to generate the sum bits in this formulation. This, of course, also generates the most significant carry out of the addition, which will be C bracket n, and that will be in the position, the nth position, if you like. Just counting them from right to left as 0 to n minus 1, those will be the proper bits of the sum, and then the nth one on the very far left would be the carry itself. So now we formed a well-formed expression we have in which S sub I is really nothing but U sub I, V sub I, or U bracket I, B bracket I, C bracket I, mod 2. So that's algebraically speaking. Now, these carries that we talked about can be computed simply by watching this sum that we basically generate throughout the computation. And the sum has to be checked whether it's actually greater or equal to 2, which is what we do here. If that's the case, then we set the next carry to 1. If not, it's equal to 0. And we do this for all the way up to 0 through n minus 1. So the carries are computed from right to left, and that, as we said already, carry bracket n is the final carry, which we also denote as the carry out. All right. Now, this is sort of the algorithm that I just talked about, which is really nothing different than what we expressed. So I'm just going to go quickly over this. So we define these vectors as our input, and they're commented out because we assume that they come into the function as they're called in. And then we compute the sum, and you notice that the carry 0 is initialized to 0. So when we do this loop the first time around, this is actually defined, but after that we define carry I plus 1, bracket I plus 1, and that's how we loop back, and then this carry gets computed every single time we do it. And then of course the sum itself is sum I mod 2. And that's a summation. That's a loop that runs up for exactly n clock cycles, at the end of which we have our sum bits and also the last carry that we want, which is Ci plus 1, which will be Cn with a bracket. Alright, so that's just the algorithmic representation of the same idea. And here's now, if you want to do it in logic circuit form, or with logic expressions like ands and ors, in which case we replace the pluses by ands. As you can see, that those are the n operation symbols. And then I'm sorry, these are the exclusive OR formulas, basically. That's what the sum is equal to, not n. I have to stand corrected. That's how you actually carry this summation. So the summation is going to be 1 if you have an odd number of ones. That's the sort of idea of this expression. So if you have 2 of them are 1, you get a 0. If none of them are 1, then you get a 0. But if you have 1 or 3 of them 1, then you get a 1. That's how the sum formula is computed. That's an exclusive OR symbol, caret. And then the CI plus 1 is basically the end combination of UI and VI, which is called the carrier generate. This whole thing is called carrier generate, and that's ORed with what's called carrier propagate, which is the rest of this expression. And that is to say, you take the carrier that you had from the prior stage and make it the carrier of the next stage, if in fact one of the bits that you're adding is 1 and the other one is 0. That is, if UI is 1 and VI is 0, or vice versa, you get that carry and then move it over. That's called a carrier propagate. Of course, you can also get a carry right within the level that your stage you actually are, and that would be called carrier generate. With both U and V bracket I bits are equal to 1, then you have to have a carry. But there's no way that you can run away from that. So that's just the same for algorithm, but written in kind of like in terms of logic gates or logic operations. All right. So now this is the circuit diagram, and you've seen most of this stuff in 244, so I'm not going to dwell too much on this. And you can see that whatever we've written in logic is just been drawn as a diagram here. These are the different stages. You got the operands coming in at the top. You got the sum bits computed at the bottom. You have the carrier generate and the carrier propagate formulations that are going to come up from these bits. For example, you take the exclusive OR of these 2 bits, and then you take the carry from the prior stage, and then you kind of like compute, if you like, by ending it with that, the carry into the next stage. The sum output will be, of course, the exclusive OR of UI and VI, which in this case is U1 and V1. And then, of course, you take it with C1, which comes into the next exclusive OR box here, or the gate. An exclusive OR is an associative operation, so you can actually just do it in 2 stages like so. And you get the sum bit and the carry bit out of here, which is basically what we computed earlier as the OR combination of the carrier generate and the carrier propagate bits, and that's how you get to generate the next carry. And this continues along a ripple path, and that's why it's called a ripple adder, this whole thing is. And then you get your adder circuit. Now what we're going to do is look at the way that we can actually possibly speed this, shorten this path a little bit, because the path length here, the carry path, is what makes this addition slow. And so we are paying attention specifically to the carrier generate and carrier propagate bits, and we write this carry, as we said earlier, as a combination of carrier generate, which is this, and the carrier propagate, which is this portion of the ith stage variables. And now we want to do this computation by simply trying to by just finding a way to compute these CIs quickly. And so the way to do that is write these C sub i's, and then make the substitutions you need. In other words, instead of writing CI here, take the CI formula, which is exactly like this with these indices shifted by 1 to the right, I minus 1s if you like, and then take that expression in. So like C1 is equal to this. C1 would have been G1 and P1 and C1. C2, that is, C2 would have been G1 and then P1 C1, but C1 is now substituted in here, as you can see. And when you make the substitution, then it expands like this, and you do the same expansion for C3 and C4. And all of a sudden you have 2-level expressions where the G sub i's and then the P sub i's are combined in this particular fashion. Like in C3 you have G2 or P2 and G1, or P2 and P1 and G0, or P2, P1, P0 and C0. So that's like the expression. It's about like a column of, if you like, or a bank of AND gates followed by maybe an OR gate. All right, so that's what you really have. So you can actually use this sort of an expression to create block carries. And the block carries, in this case, for example, if you were to have blocks of 4 stages of addition, then you can actually use C4 to compute the carries for the second block, which would be C5 through C8. And in general, you can write the expression as 4i plus 1 all the way up to 4i plus 4 if, in fact, your block width is 4 stages. So this way, you could compute things in parallel within the blocks, and this is called carrier look-ahead addition. And within the blocks, they're computed in parallel, but you still have a carrier path, but this path has been now decimated by a factor of 4 because you're taking these blocks of 4 where carries are computed in parallel. So in other words, there's been some reduction in the carry process. So here is a sort of diagram of it where the U sub i's and V sub i's are coming in to these boxes where the carrier generate and carrier propagate bits are computed. Basically, they are just AND gates and exclusive OR gates. And then once you get those bits ready, then you can do your carrier look ahead boxes, which are basically these expressions here, like this sort of a set of 4 logic expressions, which are going into each of these white boxes. And finally, you have the sum boxes. So you, in 3 stages like this way, you finish your computation, and there is a carrier chain, that's for sure, but this carrier chain is about 4 times smaller as a length, as a gate delay metric than the original one. Of course, this can be generalized, but before I do that, let me just briefly mention how this is really extended to in the form of an algorithm. And this is probably a general form where the block size is now equal to k. So you have this. First of all, you compute all the carrier generate and carrier propagate bits. All the same. They're all computed for all values of I from 0 to n minus 1, and then you now have to compute basically the compute carries across the blocks, and then compute within the blocks, compute them within the blocks. And then that means like the blocks are of size k. You can see that right in this for loop. So the k determines the size of the block. In our example earlier, our block size was 4, like here. Basically, that's what this is. Now, in this situation, k is equal to 4. So in this program, we are having blocks of 4 stages, if you like, and so we are computing these carries within the blocks, and then once we get that, of course, we then have the product terms computed, and those are the expressions that we have to get in order to generate ultimately the carries, the P sub I terms, as this would be. And once we get those P terms, then we can actually compute the carries within each of those blocks. And then once we finish this process, then the bits for the sum itself are generated strictly by taking the P sub i's and the C sub i's. P sub i's will be computed in here, C sub i's get computed in here, and that completes the computation. So this is the same thing as this diagram, which is like written in a sort of a way that you could see how the code simulates this process of addition. So that is really carrier look-ahead addition, and you can see that when we create these k segment or stage blocks, we are having a total of n over k blocks from right to left, and so whatever the delay through each block is going to have to be multiplied by n over k because we have so many blocks, and that will determine the delay through the entire circuit. So basically, since we are doing these additions within a block of let's say k bits is what we're doing basically, then the complexity will be order log k, and the total delay will be n log k over k. And so as a result of which we get basically log n as our k tends to n. So that's how we get to compute this. The log k, if you're just wondering where how we get this, is obtained by the fact that we are computing these k-bit additions by essentially doing parallel carrier generation, and we're limiting ourselves to as you'll see, in fact, on the next slide possibly, or the slide after the one. Before I go there, let me just bring this up here. So what we're really doing here is this, if you want to really know what this is happening, what's going to happen here. This is what we're computing basically in log k time. So for that to happen, we have to take, for example, this part of the expression and do it in binary tree fashion, like combine these two together, maybe leave this alone now, combine these two together, and then do this in log stages. So if it's 5, it's going to have to be 3. If it's 4, it's going to be 2 levels. And then once you do that, then you got the OR gate situation, and then you do the other binary reduction. So if in fact you're doing this for k-bits, then the number of terms that you're going to generate will go up to about k or k plus 1, and you'll see this. And then because of that, that log k term comes into this situation here. And so when you replace k by n, these n's cancel out, and then you get the log n time for the addition. But by the same token, you will see that in fact doing this for within each block, you're going to require binary trees of size k, and that will ultimately push your complexity to n squared. When you actually compute this, you will see this in just a second. I'll get there on the next slide or two. So to produce a circuit where, with order and logic gates with constant fan-in, that is to say, constant number of inputs, and do it also in log n time, we need what we call the Brent and Kung, or sometimes called Fisher and Ladner, because these are the two research teams that actually solved this problem around the same time. I would say Brent and Kung probably more deliberately, specifically focusing on the actual problem, whereas Fisher and Ladner sort of working on the prefix end of things, which is basically a more general version of the same problem. So let me just say one more time that typically the carry path is n stages. For an n-bit addition is what this is. And so you have some carry out, which needs to be relating all the carry generate terms and the propagate terms, which are these, along with the carry in to come up with a carry out. Because along the way you have all the other carries computed because you want to compute the intermediate sum bits. Now, and you can easily determine, and I can show you an example on the next one, that the number of terms in this sum of product expression we have to write will have actually products that may just have between 1 and n plus 1 variables. So here's an example. N is equal to 4, carry in is equal to C0, carry out is C4, and the highest term is this, and you can see that there's a 1 term here, a singular term, and there are 5 terms here. Okay, this is actually shifted a little bit. I should just bring this in box. This must come up like this, and maybe, okay, widen it like this. There it is. So it's 5 terms if you count them really. 1, 2, 3, 4, 5, and then there's a 1 term. So in general, this is what you would really need to do to compute C4. You need basically a circuit like this, where you have the binary trees to compute the AND gates, and you have a binary tree to compute the OR gate, basically. And you're just having binary trees because you don't want to have the fan-in grow on you. As you can see that, the number of bits we said already will just go up to n plus 1 terms, and in order to contain it, you just have to use 2 input AND gates here, 2 input AND gates, and so on. And same way, 2 input OR gates. So this is just for 1 carry, and you can see that a single carry here is going to dictate to you basically a number of gates. Let's just carry computation here is going to require you to compute basically with binary trees that will run up to size n plus 1 terms. So that's going to take you, n gates here. And of course, n minus 1 may be some number, n minus 1 gates here, let's say. It's actually n plus 1 input, so it'll be n gates here. It's, n, but that's a binary tree of depth log n. And somewhat, order n minus 1 and n minus 2. So you're adding these numbers, so you can see that you get to go to order n squared easily with this solution. So so now the question is, can you really keep it to order n complexity as well? Like I said here, it's going to go up to order n squared because you have about n of these. When you go to the big size here, n of these n gates, and that's going to require you about order n squared. That's the buildup of this expression anyway, gates. The depth or the gate delay is not a problem. It's order log n. It's just like the size of the circuit grows too big. And so to do it in order n, gate complexity, that is number of gates being order n, Brent and Kung came up with this prefix adder concept, which is basically like this. We need an associative operation, which is kind of critical. And in this associative operation, we need to have our C sub I, generated by this sort of an expression. So that's what happens here. As you can see, he defines an operation, or they define an operation, where you take G sub I minus 1 and P sub I minus 1, and then use it with the circle operation, which is our key operation here, and put on the right-hand side Ci minus 1 and then Pi minus 1, this capital Pi, which I will explain what it is in just a second. And where this circle operation is defined as X or Y and W, and then comma Y and Z, which is what the product of these two. So you can see that if you just substitute, if you just use this expression on this, you will have G sub I or P sub I, G sub I minus 1 or P sub I minus 1 times C sub I minus 1, which is what this is that's ended together. And of course, the capital Pi minus 1 will be the product of this term with this term, the second term. That is P sub I minus 1, smaller p, lowercase p, multiplied with uppercase Pi minus 1. That's what's going to give you P sub I, uppercase. So associativity is secured easily if you just really follow this logic and just do the actual steps. You will convince yourself that in both cases, whether you sort of like take the latter two pairs first and then the first pair last, or the first two pairs first and then the latter pair last, in the way that you compute this circle operation in these three variable forms, you will see that in fact they come out to the same expression. I just leave this as a small exercise to do this on your own because it's actually obvious. So the circle operation is associative, and that's what is key, because what that does, it allows us to write a bunch of expressions like this, where we have the carrier terms expressed in terms of the carrier generate and carrier propagate terms by this associative operation. Now you see the circles are going to come into each and every one of these. And so now we really converted this expression that we had some time ago here, like these forms of expressions where you have the AND and OR gates, like here's an OR and there's an AND, OR, AND, OR, AND. All of that has been now converted into one simple operation, which is associative. Only circles. You can see that these are the same expressions. Of course, we have a second term here, second index position, but we're interested in these C sub i's. And our carries are going to be generated simply by taking these, in any order we like, G1, G0. Like when I were to compute this, if I start out on the left, it'll be G1 or P1, G0, and then I can then take it with the next computation circle. So that's how it's going to go. I can actually combine them in any order because they're associative. And so this associativity is very powerful because it's going to let us compute all of these carries in a circuit that's going to have log n delay, gate delays, and also order and complexity. By the way, this is called a prefix expression. When you have a bunch of expressions like this where the next expression is or the prior expression is a prefix of the next, like this expression is, in this situation, actually a prefix, if you like. I would probably think of this as a postfix, but just this whole C1, P1 is, when you write it out like here, it comes in here, so this expression kind of is expressed in terms of this times this, and then this expression, of course, is it's a sub-expression. Maybe I should call it a sub. There's a sub relationship. Like this one is a sub-expression of this. This one is a sub-expression of this. Both of these are sub-expressions of that, and so it goes that way. So now we could actually sort of simplify these terms by just writing them in terms of x sub i's, and then I should have actually written this a little more cautiously here. Let me just say this. I don't mean actually in parentheses here. I just meant, let me just quickly fix this. X sub I is, as a matter of fact, equal to this. Okay, that's a little better. Yeah, there it is. So we're looking at this expression. These x sub i's are really our lowercase g sub I and p sub i's. These are the carrier generate and carrier propagate expressions in our original circuit. Basically, these terms are. And you can see that all the carries are going to be computed in terms of these carrier generate and carrier propagate bits. That's all it is. And now that we have this, we want to know how we can implement this. So the way to do that is to use what's called a Brandt and Kohn prefix network. And so this prefix network is essentially going to take these inputs, which we call x sub i's by this time, just to simplify things a little bit. In other words, we call these things like x0, x1, x2, and so on, and that's they are defined here. And so therefore, this set of expressions is equivalent to this, if you like. Okay, the left-hand side is the same. These expressions stay the same, if you like, except we just introduce C0, gamma 1, but the rest of it is basically like this, and we notationally just simplified it to C1, P1. It was bracket C1, P1. Now it's just subscript C1, P1. Same thing. And so we're looking at this. What we're doing is, if you just look at it very carefully, a total of n inputs are going into this, or actually, yes, n inputs, because we start out with -1, go up to n minus 2, so n minus 2 minus minus 1 plus 1, that's equal to n. And that set of inputs, all n of them, exactly half of them, as you can see that we skip every other one, are pushed into this box. They go into the box. They actually go into the box. Like this one goes into the box. First one doesn't, the next one does, the next one doesn't, the next one does, and all the way up to the last one. Last one does, but the one prior to it doesn't. The ones that really don't go into the box, they just cross over the box. They're just not subjected to what this box does. They come straight out of whatever they were. They just maintain their values and they come down. So, and then they are subject to some further operations in here where you see our circle operations kick into action, both in the front end and the back end of this box. So whatever we're doing, we're taking only half of these inputs and subjecting this box to them, and then producing as many outputs, and then the other half of the inputs, they get processed by these circles, and then they get processed by these circles. In other words, once in the front and once in the back. And that's what the circuit does. So miraculously, if I could say, they in the end compute all the C sub i's and the P sub i's that we want, the uppercase. And because this is a prefix circuit, which will simply compute x minus 1 here, and then x minus 1, x0, and then x1, x0, x minus 1, and then x2, x1, x0, x minus 1. Essentially, it's a recursive construction. The bigger box is going to be constructed like this, but this box inside will be constructed exactly the same way, where we're going to decimate the number of inputs from n over 2 to n over 4. The other n over 4 will go through the structure. So that recursive construction is what makes this thing work. As we explain, I guess, this a little more in class. So when you compute the gate complexity, of course, it has to be that the number of gates here is going to be n minus 1, if you just count them. This will be n over 2. And then this will be n over 2 minus 1, because we're just basically taking two things at a time and then generating one out of it, which is one circle goes between two wires. That means n over 2, about n over 2 here. And then about n over 2, but because we start one step later, that gets to be n over 2 minus 1. So together, n over 2 plus n over 2 minus 1 gives you n minus 1. Circle gates, we call them. Of course, each circle gate contains inside just an OR gate, AND gate, and another AND gate, if you just remember it. Looking back at this expression for a second, right there. OR gate, AND gate, another AND gate, right there. That's what the circle does. And so now we have that. We can write this formula. And with the initial value of C, that is 2, when 2 is down to, n is down to 2, is going to be just like a 2-input circuit where you can actually make it equal to 1, the complexity, just a single gate. And then, of course, that will give you this complexity, 2n minus 2 minus log 2n. Order n is what I should have written. We actually just seal that, make it equal to order n. All right. And this is also order log n. While I'm actually here, make it order log n. Log n. There we go. So that takes care of that. And now, so the gate delay, of course, is, if you look at it carefully here, the circle gates have a constant delay. It's just like a two-level circuit, that is. Basically, AND gate, again, looking back at this expression, I mean, this is the more complex part of it. This is just a single-level AND gate. And here we have an AND gate followed by an OR gate. So it's a two-level circuit. So we can definitely write this expression here, that the complexity is going to be equal to 2 times, that is 1 here and then 1 down there, that's 1 over 1. Okay, so the 2 steps, like, go through this once and then here, and whatever else is going to come in between, that's Tn over 2. So Tn over 2 plus 2 tau 0, and then tau of 2 is equal to tau 0, just a single gate, whatever it is, and then this gives you a Tn of 2 t tau 0 log n, that's order log n. So we got ourselves an order n gate complex circuit with order log n gate delay is what we have. And here's sort of like how you would really visualize this if you were to do an 8-input prefix circuit, as you can see how that is. Sorry about this. So this is the yellow box, is the big box, inside of which we have the gray box, and then we have these so-called circle gates. And then the gray box is the half-size one, where we go into with these 4, 1, 2, 3, 4 inputs. The other ones bypass it. As they bypass, they come out here, and then they're subject to these 3 operations, 3 circle gates. But the gray box is itself divided into 2, where you have only 2 inputs left that are going to go into the box. And the other ones that actually are going into this box, of which there shall be only 4, will have to be then just run through. And then this whole thing, repeats another box, which is the brown box. So I'm showing you exactly how you would actually recurse this. And I also want to show you the binary trees that develop. This is sometimes how people draw this. Here's a binary tree, if you just imagine this. And then here's another binary tree. So sometimes people talk about a downside up and an upside down binary tree, or just a regular binary tree, followed by or upside down binary followed by a regular binary tree. This is basically what this prefix circuit is. Sometimes people draw it that way, without relying much on the recursion. But the overall circuit itself is, now we can wrap it up, is going to basically have the U and V bits coming in to an AND array, and then onto an OR array, exclusive OR array on this side, and then collectively they have the carrier generate and carrier propagate bits, and now they go into the Brandt-Kong prefix circuit, and this circuit then takes them up and generates the carries, and of course we have the PIs generated already. We take the two together and then subject them to another XOR array, and you get the sum bits. This is the one that takes log n time. Everything else is just a bank of arrays, a bank of gates, nothing else. Okay, here's one an array, OR array, and an OR array. So these are constant delay, and the only thing that really makes matters go up to log n in terms of gate delay is this circuit. And so the whole thing is order log n. And again, the complexity-wise, this is order n. This is also order n because you're just simply taking n gates, and then n exclusive OR gates, and another exclusive bank of n exclusive OR gates. So you have three of these plus the n, order n. Everything is order n. The delay is order log n, and that's what we wanted to do, and that's what we promised to get, and that's what we get. And then so the last thing that I want to say is that subtraction is just a 2's complement addition, so there's really no need to cover it separately. Just take the Brandt-Kong adder and just add in front of it a bank of exclusive OR gates up here, if you like it, to the adder. If you're going to subtract, for example, V from U, just simply subject the V's to the exclusive OR gates, and then stick a 1 in as a carry in other words, make the C0 equal to 1. You get yourself a Brandt-Kong subtractor, and subtractor would also do the same thing, in terms of delay and complexity, order n gates and ordered log n gate delays. So that's really what high-speed addition is all about with this particular sort of algorithm that we covered in this video, and that is Brandt-Kong adder. So that brings us to the end of this video coverage, and I will upload this and so that you can actually view this. Now after this I'm going to also go ahead and do the multiplication, but until then take care, and I'll see you in class on Wednesday.